All right, so here we go with lesson 6 EE3. And we are going to talk about different properties that allow us to create equivalent expressions. Right. So we've talked about the commutative property that allows us to move numbers around when we are adding or multiplying. And the distributive property is when we are going to distribute a number that is outside of the parentheses. So if I'm taking like 2 times the quantity 4 plus 5, I can actually distribute that 2 to the 4 and the 5 using multiplication and create an equivalent expression that's going to equal the same thing as if I were to solve it using the order of operations. I have the associative property, which allows me to move my groupings if I'm multiplying or if I'm adding. I have the identity property. Now there's 2 different identity properties, one of multiplication, and that's where it's telling us that anything times 1 is the number itself. It allows it to keep its identity. Or the identity property of addition. Now in that case, that number is 0. So they're the same idea, it's just that the number is different. So if I multiply by 1, the number stays the same. If I add 0, the number stays the same. I can also use combining like terms, keeping in mind that like terms have to be terms that have the same exponent and the same variable. All right, so taking a look at this, we are going to use combining like terms on this first page to go ahead and create an equivalent expression to those listed. So here I have a 7x, a 2x, and a 5x because each of these has a variable that is x, and none of them have exponents. They are all like terms, which means I can go ahead and combine each of them. So here I can take 7x and add 2x to it. So this is like saying I have 7x's here and I have 2x's here. If I put them together, I get 9x. And then bring down the plus 5x. Again, I have an x and an x, no variables, so I can combine these as well, and I get 14x. So I actually created 2 equivalent expressions here to the one listed above, because this is one expression, and this is a second expression. All right, if we're looking for the most simplified, then number 2 is going to be our answer. If we're just looking for equivalent, then number 1 is going to be our answer. Now, what it means here is these 3 expressions should all give me the same answer if I plug in something for x. So for example, let's plug in 2. So I have 7 times 2 plus 2 times 2 plus 5 times 2. So I would get 14 plus 4 plus 10, which would give me 18 plus 10, which would give me 28. So if I use the first expression, I would get 28. If I use the second expression, if I did this correctly, I should also get 28. So I would do 9 times 2 plus 5 times 2. 9 times 2 gives me 18. 5 times 2 gives me 10, which gives me 28. So far, so good. And here I would do 14 times 2, which gives me 28. So that proves to me that each of these 3 expressions are equivalent. Looking at the next expression, so first I'm going to go through and I'm going to find my like terms. I have 8a and 2a that are like terms, and then I have 11t. 11t doesn't have any like terms, so I cannot combine it with anything. It has to stay as it is. Now, looking here, I have 8a and I have 2a, but they're being combined by this subtraction right here. So in order to combine them, I would have to take these 8a's and subtract 2 of them. So in that case, that would give me 6a plus 11t. And again, you can double check that by plugging in a number for a and a number for t. So for a, let's go ahead and just put 1. Let's make it simple. And then for t, let's go ahead and plug in 2. So if I plug in 1 for a, I'd have 8 times 1 plus, and plug in 2 for t, I'd have 11 times 2 minus 2 times 1. Whoops, there we go. So I have 8 plus 22 minus 2. 8 plus 22 is 30. Subtract 2, I get 28. Okay, so then now let's go ahead and see what I get with 6a. So 6 times 1 plus 11 times 2. 6 times 1 is 6, plus 11 times 2 is 22, and I get 28. Thus proving that my two expressions right here are equivalent. Now with this next one, we are going to go ahead again and find our like terms. I want you to take a minute and see if you can find your like terms, and then we'll go from there. All right, so here I have 13a, and I'm actually going to change the color of my pen since it's red and it's really hard to see. So I have 13a and 8a that are like terms, and that's actually it. Now I know I have this a here, but it's a squared, and since there's no exponent here and no exponent here, I cannot combine that with the other a's. It has to not only have the same variable, but the same exponent. So here I can combine the 13a and the 8a, but again, it's combined by subtraction. So you're looking at the operation that's right in front of the one that you are going to combine. Later on down the road, we can talk about how this all would change to addition of the opposite. And so we can move numbers around however we want. But since we're really not into the negative number stuff just yet, just know that to combine them, you need to look at that operation right in front of what you're going to combine to the first one. So here I have 13a minus 8a, and that gives me 5a minus 7a squared plus 2. So again, these two things should be equivalent, these two expressions. To check it out, let's plug in a variable. So let's do 13. So we're going to do a is equal to 1 again. Just make life easy. Why do we have to choose a big number? So 13 times 1 minus 7 times 1 squared plus 2 minus 8 times 1. Okay, so 13 times 1 is 13. 1 squared is 1, so this would be 7 times 1 plus 2 minus 8, because 8 times 1 is 8. So now we know using the identity property that these numbers here, so 8 times 1 and 13 times 1, should have just stayed as 13 and 8 because we were multiplying by 1. And then here we also know that 7 times 1, using the identity property, is going to stay the same. So I can just pull everything else down and work my way across. So 13 minus 7 is 6, plus 2 minus 8. 6 plus 2 is 8 minus 8. I should get 0. So then now, if I use my other expression, if I use 5 times 1 plus 7 times 1 squared plus 2, I should get 0 if my expressions are equivalent. So I get 5 plus, well, in here we know that this is just going to stay as 7, so I'm going to skip a couple steps here just because I want to save some space because I'm running out of it very quickly. And I should actually be subtracting those two things, not adding. Fix that real quick. There we go, that should make sense. Plus 2. Now, 5 minus 7 is actually going to give us a negative 2, and when I add a negative 2 to a positive 2, it's going to give me 0. Once again, giving me equivalent expressions. Okay, so we've talked about combining like terms, and now we're going to talk about using the distributive property. So in this case, the distributive property is when you have a quantity, so something inside the parentheses, and you're multiplying it by a number. So in this case, I have the quantity 2x plus 4, and I'm multiplying it by 7. What the distributive property allows me to do is distribute that times 7 to the 2x and to the 4, therefore essentially breaking the parentheses. So then this would become 7 times 2x plus 7 times 4. I keep the plus sign because it was a addition problem up here. 7 times 2x I can combine because I'm just using multiplication. If it was 7 plus 2x, I couldn't do that. So I would get 14x plus 7 times 4 is 28. I can't combine any further because it's using addition. There we go. It's using addition, and I don't have an x here. So 14x plus 28 is equivalent to 7 times the quantity 2x plus 4. Again, we can go through and we can put in our value for x and check to see if our answer is correct. So 7 times, I'm going to use 1 again. So 7 times 2 times 1, which is 2, plus 4. So this is 7 times 6, and that gives me 42. So if I take 14 times 1 and add 28 to it, that gives me 14 plus 28. 4 plus 8 is 12. Carry the 1 is 42. This is the last time I'm going to double check to make sure that my answers are correct. When you're asked to prove that your expressions are equivalent after you've found them, this is how you're doing that. You're plugging in a value for your variable and showing that you get the same answer regardless of which expression you use. So I'm going to distribute again. So I have 2x times 5x and then 2x times 9. Notice there's no multiplication symbol here. It's because there's a parenthesis that tells us that we're multiplying. So here I'm going to do 2x times 5x plus 2x times 9. Now, looking at this, I have 2 times 5, which is 10, but then I have x times x. Remember, repeated multiplication gets turned into exponents. So x times x is going to be equal to x squared. So this would give me 10x squared plus 2x times 9 would give me 18x. I cannot combine any further because this is x squared and this is x. So my equivalent expression would be 10x squared plus 18x. Now we're going to work in reverse of the distributive property, and we're going to factor. So when we're factoring, we're going to use typically the greatest common factor to divide our expression by. Now we only do this when we have things that are that we want to maybe make it a little easier to multiply or something to that effect. All right. So here I have 36 and 12. So if I'm not sure, I can take 36 and 12 and put them in my ladder, and both of them are divisible by 6. 36 divided by 6 is 6. 12 divided by 6 is 2. Both of them are divisible by 2. 6 divided by 2 is 3. 2 divided by 2 is 1. Their common factor is 1. So I'm going to multiply these three numbers, and I'm going to get 12. So the GCF of those two things is 12. So what I'm going to do is I'm going to take 36 and divide it by 12, and that gives me 3. And then 12 divided by 12 gives me 1. So when I divide out that 12, it's going to come outside of the parentheses. So here I multiplied and I shared that 2x and that 7. Now it's basically like I'm unsharing it. I'm undistributing it, but we call that factoring. Now the other common factor here is that both of them have an x. So I can actually pull out the x as well. After I did the 36 divided by 12, I was left with 3. I would keep the subtraction sign, and then when I did 12 divided by 12, I was left with 1. And I have to put that 1 in there because if I don't, my expression is no longer equivalent. So by using factoring, I'm finding that 12x times 3 minus 1 is also equivalent to 36x minus 12x. We could even go further down the road. Now, if it asks me just to factor, this is all I want. If it asks me to give another equivalent expression, I could say that 12x times 4 is equivalent. I could also combine like terms and say that 36x minus 12x, which would be, 3 minus 1 is 2. My goodness. No adding. We're subtracting. So 2. And then here, 36x minus 12x is 24x. So I have now made 3 expressions that are equivalent to that 36x minus 12x. Again, this is factoring. And these two are combining like terms. All right, and then your last problem here that we're going to go over, we have 35x minus 70. So finding the common factor between 35 and 70, yes, we could say that it's 5 and say that 35 divided by 5 is 7. And then 70 divided by 5, so 5 goes into 7 one time, and I have 20 left over, so 4. So if I divide both of these by 5, I get 7 and 14. Notice both of them don't have x's, so I can't pull that x out. Here, I could pull out the 5, and I'd be left with 7, where the 35 was, so 7x, minus, and then I'd be left with 14, where the 70 was. Now, what you should notice here is that 7 and 14 still have a common factor of 7, because 7 can go into 7, and 7 can go into 14. So it's not that I'm incorrect in creating an equivalent expression. This is equivalent, but if I'm asked to use the greatest common factor, I did not fulfill all the requirements. I still have to pull out another 7. So what that means is I can go through and do this again. If this still can be divided by 7, so 7 divided by 7 and 14 divided by 7, I can multiply these two things, and that would be the factor that I'd want to pull out. So in this case, 35 would be my greatest common factor. And when I did 7 divided by 7, I'd be left with 1x. I could even just put x. And then when I have 14 divided by 7, I'm left with 2. And now I have 35 times the quantity 1x minus 2. You could also have done that in just the very first step and divided both sides by 31 or 35. But I wanted to show you that if you see that inside of here you still have a common factor, you still have a ways to go, and you don't have to start all over. You just have to take whatever you divide it, whatever you can still divide by, and multiply it by whatever is on the outside.